Hello guys, how you doing? This is the second session of instructing fluid mechanics 1, chapter 1, section 1, 4219. Follow me with the instruction. So, as I told you, I'm gonna instruct the fluid mechanics 1, chapter 1, part 2, which are the sections from 1.4 to 1.9. This is my full name, Amirraza Talaqat. I'm Iranian, and this is my contact email, amirrazatalaqat@gmail.com. I'll be delighted to have a contact with you. Don't hesitate to ask your questions or any further information you need. I'll be answering you as soon as possible. So let's go for the instruction. The titles I'm going to talk about are measures of fluid mass and weight, ideal gas law, viscosity, compressibility of fluids, vapor pressure, and surface tension. The first title is measures of fluid mass and weight, density. Let me bring my notes in order to not forget to tell you all the details. No. So, density of fluid. Let me just tell you that I'm gonna read through whole the text, and I'll give you the details and notions I've instructed at the end of my reading. The density of a fluid is designated by Greek symbol rho. Is defined as the mass per unit volume. In the BG system, rho units of slugs per cubic feet. And in SI, the units are kilogram per cubic meter. The value of density can vary widely between different fluids, but for liquids, variations in pressure and temperature generally have only a small effect on the value of rho. As it said, in the liquids, we have so many fluctuations due to temperature variations in density magnitude. As you will see in figure 1.3 here, as the density, as the temperature increases, we have a decrease in magnitude of density. The magnitude of density for water at 40 degrees Celsius is going to be 1,000 kilogram per cubic meter. But in gases, this effect of variations is somehow low. In further details, if you want to go through, you can refer to tables 1.5 and 1.6 at the end of the book, which I have provided them in the Telegram channel. Unlike the density of a gas is strongly influenced by both pressure and temperature, and this difference will be discussed in the next section. Unlike liquids, the density of a gas is strongly influenced by both pressure and temperature, and this difference will be discussed in the next section. I excuse you guys, I might have mistaken. In gases, as we're going to be through it by terms of molecular structure, difference in pressure and temperature has a really good, has a wide effect and impact on the gas's density. The specific volume is the volume per unit mass and is therefore the reciprocal of the density, that is nu, 1 over rho. This property is not commonly used in fluid mechanics, but it is used in thermodynamics. as you may have been through a course, thermodynamics, in that course, there's definition by specific volume, which means reverse of the definition of density. If we have m over v, which is defined as density, the reverse of that, which means 1 over rho, we're going to have v divided by m, which gives us the specific volume as it has said in the PowerPoint slide. That's it. Let me think about that. It might be good if I provide you a written text and give you the details there. Follow me with the written text. Welcome guys to this section. As I told you, when we have a definition of a density, we have this. Rho is equal to m divided by v. When we reverse it, it is gonna be 1 over rho, which is equal to v over n. This equation is gonna be a small v, which is a specific volume. Specific volume. Welcome back. We're on the second section of measures of fluid and mass weight. Specific weight. The specific weight of a fluid is designated by the Greek symbol gamma. It's defined as its weight per unit volume, as we have here. Just as density, it is used to characterize the mass of a fluid system. The specific weight is used to characterize the weight of a system. In the BG system has units of pound per cubic feet, and in SI units, it is Newton per cubic meter. Under conditions of standard gravity, G is equal to 32.174 feet per square second and equal to 9.807 meters per square second. Water has a specific weight of 62.4 pound per cubic feet and 9.8 kilonewton per cubic meter. Tables 1.5 and 1.6, as I told you, list values of a specific weight for several common liquids based on the standard gravity. More complete tables for water can be found in Appendix B, Table B1 and B2. When I was studying fluid mechanics 1, the definition they told us about the specific weight is it was exactly capital W divided by M, because in that case, no, let me just remind that. Yeah, that was correct. Because as you know, the capital W is weight, which is equal to mg. M is going to be attributed and divided into multiplication of density to volume. If we write this down, rho Vg, which is equal to the, capital W weight, and divided by the V, we're going to have a specific weight, which is gamma here. It is rightly instructed. In the next point, we have specific gravity. The specific gravity of a fluid is designated by as S in SG units, is defined as the ratio of density of the fluid to density of water at some specified temperature. Usually the specified temperature is taken as a 4 degrees Celsius, which is equal to 39.2 degrees Fahrenheit. And at this temperature, the density of water is 1.94 slugs per cubic feet, or 1000 kilogram per cubic meter in equation 4. Specific gravity is expressed as here. Sg is equal to rho of the fluid divided by rho of water at 40 degrees Celsius. Since it is the ratio of densities, the value of Sg does not depend on the system of units used. When we divide the density of a fluid to the density of water at 40 degrees Celsius, we just have the constant. As it said, we don't relate it to units because the units are going to cancel each other. So, in here, in these pictures, you can get the concept of specific gravity, which is illustrated in this picture. Here we have example 1.3, which is related to density. The compressed air tank shown in figure 1.3a here has a volume of 0.84 cubic feet. The temperature is 70 degrees Fahrenheit and the atmospheric pressure is 14.7 psi absolute. When the tank is filled with air at the gauge pressure of 50 psi, determine the density of the air and the weight of the air in the tank. I'm gonna solve it for you in the written text, but let me just tell you that when we have a gauge pressure here and absolute pressure here, there might be some details about it, which I'm going to instruct it in this session. Don't worry about it. Let's follow me with the written text of example 1.3. Welcome guys to this section. As I told you in previous minutes, we're going to solve example 1.3. Let me just specify the given parameters. We have a volume of 0.84 cubic feet and temperature is 70 degrees of Fahrenheit, and also atmospheric pressure, which is P of reference, PA, is 14.7 psi absolute. I'm going to demonstrate this in following sections of this instruction, but for now just know this. I'll specify the absolute and its details. The question wants us to determine the density of the air and the weight of the air tank regarding of P gauge. P gauge is 50 psi's. So, according to equation 1.8, we have rho is equal to P divided by RT. For this equation, we're going to have rho is equal to 50 plus 40.7 which is P gauge plus P atmosphere, which is here. Why we have added these two up, I'll give you the details, but just for now, know that we use, as I told you, we use a P absolute here. What is P absolute? It's going to be demonstrated. I'm not going to repeat it again. We have a units of pound per square inches here. We have to give it to pound per square feet. So we're going to multiply this by 144 cubic inch is 1 cubic feet, because each 12-inch is 1 feet. When we turn it to power 2, it's going to be 144 square inch is equal to 1 square feet. The R is 1,760 feet pound per slugs. Degree of Rankine, and in order to have the temperature in the Rankine scale, we have to add it to 460, which is going to be degree of Rankine. Doing the calculation, we're going to have rho is equal to 0.102 slug per cubic feet. But when we're going to find the weight, we have to have that equation like this, which is equal to weight is equal to mg, which is rho vg. As a result, we have a weight is equal to rho, which is 0.0102 slugs per cubic feet, multiplied by, we had the volume of 0.84 cubic feet, multiplied by G, which G in feet scale is going to be 32.2 feet per square second. We have, this is going to be canceled by this. So we have, excuse me, 0.276 slug feet per square second. This is going to be pound, which is 0.276 pounds is equal to weight. Welcome back, guys. We have just reached to ideal gas law. Gases are highly compressible in comparison to liquids, with changes in gas density directly related to changes in pressure and temperature through the equation. Before that, we are in the right course. Yes. Through the directly related to changes in pressure and temperature through the equation here. You know, you may have seen it in heat transfer and thermodynamics either. But here we just have this form of equation. Rho is equal to pressure divided by RT. It is commonly termed the ideal or perfect gas law, or the equation of state for an ideal gas. You know, guys, when we are gonna solve everything based on pressure, this equation embeds in it. So pay attention here to learn it very carefully and sufficiently. It is known to closely approximate the behavior of real gases under normal conditions, when the gases are not approaching liquefaction. Pressure in a fluid at rest is defined as the normal force per unit area exerted on a plane surface, real or imaginary, immersed in a fluid, and is created by the bombardment of the surface with the fluid molecules. So, the main point here is that you have to notice this equation as equation of state. When you hear equation of state, you have to remember this equation, or gas law, or ideal gas law. Ideal gas law. So let's go on. From the definition, pressure has the dimension of FL to power minus 2. As we have the force divided by area, we have F divided by area. And area has a unit of square meters, which is going to be L2. When we get it to the top, we have FL to power minus 2. And in BG units, it's expressed as pound per square feet. Pound per square feet is going to be attributed as this, or pound per square inches, which is PSI. And in SI units as Newton per square meter, which is Pascal. And pressures are commonly specified in pascals. The pressure in the ideal gas law must be expressed as an absolute pressure, denoted as ABS, which means that it is measured relative to absolute zero pressure, a pressure that would only occur in a perfect vacuum. Standard sea level atmospheric pressure by international agreement is 14.696 psi absolute, or 101.33 kilopascals absolute. For most calculations, these pressures can be rounded to 14.7 psi and 101 kilopascals, respectively. In engineering, it is common practice to measure pressure relative to the local atmospheric pressure, and when measured in this fashion, it is called gauge pressure. Thus, the absolute pressure can be obtained from the gauge pressure by adding the value of atmospheric pressure. For example, as shown by the figure here, of a 30 psi gauge in a tire is equal to 44.7 psi absolute as standard atmospheric pressure. More complete tables for air at standard atmospheric pressure can be found in Appendix B, tables B3 and B4. You know, guys, we have known something really important here. Let me just demonstrate it to you in a written text. Follow me with the written text. Welcome, guys, to this section. As I told you in the previous minutes instruction, as well as previous example, we have a formula which is P absolute is equal to, is equal to P gauge added to P ambient or atmospheric. In thermodynamic, in fluid mechanics, we most of the times use this equation due to the fact that building the equipments and instruments are completely regarded this formula. But in thermodynamics, we're just going to use this amount. The thermodynamics P is always P absolute, but in thermodynamics we have to regard P gauge as well due to reasons I told you. By way of example, we have a gauge here which is giving us 32 psi's. This is gauge pressure, which is going to be also regarded as psig. When we want to have the absolute pressure, we have to define the P atmospheric or P ambient. This is ambient either. The P ambient or P atmospheric is 14.7 psi or 101.325 kilopascals. So, as we have psi here, we are gonna add 32 plus 14.7, which is gonna be equal to 46.7 psi's, which is gonna be also psi absolute, psia. So be careful about these two, this and this. When you want to have a psi absolute, you have to add psi gauge, add to P ambient, because this pressure is the vacuum pressure regarded to vacuum area. In thermodynamics, we always have regarded that P absolute is regarded to is calculated from vacuum pressure. In more accurate meaning, we have added this psi gauge to P ambient in order to have the absolute in thermodynamics. But in fluid mechanics, we have to do this because most of the times we are going to have the psi gauge and we have to provide psi absolute. So go for the further instruction. Welcome back, guys. Let me just tell you the little text here and table here, and we're going to follow the next slides. The gas constant R, which appears in equation 1.8 here, it depends on the particular gas and is related to the molecular weight of the gas. In the ideal gas law, absolute pressures and temperatures must be used. So, guys, pay really careful attention here. If you're gonna apply this equation into your solution, pay attention to this pressure. It must be absolute. Neither gauge nor neither gauge nor atmospheric pressure at sea level. Just absolute. Please be careful about that. Tables 1.7 and 1.8 have demonstrated some approximate physical properties of common gases at standard atmospheric pressures in BG units and SI units. In this picture, we have a 0 here, but this 0 here means standard, let me just verify it. The 14.7 here is the standard sea level at atmospheric pressure, which is attributed as 0. When we have verified that we have 13 psi here, it means we have 30 psi gauges, 30 psi gauges, which is going to be added to 14.7, and at the last we have 44.7 absolute pressure. So we have got the most highlighted subject, viscosity. The properties of density and specific weight are measures of the heaviness of a fluid. There's apparently some additional property that is needed to describe the fluidity of the fluid. Guys, when we say weight, density, we have somehow interpreted its physical manner. But in terms of fluidity and molecular structure or molecular behavior, we have to know more than that, which we introduce viscosity. As you see here, let me just bring my, let's see here. Yeah, we are on slide 8. Slide 8, yeah. It means that, yeah, you're on this right course. Guys, when we are here, as we move this plate by getting regard this, that, by getting regard of fixed plate here, which means no velocity is exerted here. When we move this plate, some sort of shear forces are going to be exerted on this part in somehow constant slope, but in real manner it's some sort of hyperbolic. Assuming the solid was mechanically attached to the plates, we note that to resist the applied force, closer inspection of the fluid motion between the two plates would reveal that the fluid in contact with the upper plate moves with the plate velocity u, and the fluid in contact with the bottom fixed plate has a 0 velocity, which means no slope condition. As you see, guys, in this picture, when the fluid is gonna be passed over here in these bottom layers, the fluid is gonna be attached to the thing, as there is no velocity in real bottom, which means u is equal to 0 on the surface. But in order to introduce you the equation 1.9, which means which is tau is equal to mu du over dy, and shear strain here, shear strain rate here, I'm gonna provide you the handwriting text, and in that I'm gonna give you the whole detail of getting out of this definition in detail. Follow me with the written text. So, welcome guys to this section. Let me just give you the details of a formula of shear stress. Assume that we have a container like this, and there's a fluid over here. The bottom layer is having no slip. Why? I'll give you the details in further. No slip condition. Assume that we have an iron plate here. When we give a velocity of that and pull it to the right side here, we have this condition at first, but in the second condition, when it's going to be here, we have this condition. This is a hyperbolic manner of shear stress, but for easy calculation, we're going to have it as a constant slope, like this. Why? Let me just do the calculation for you. When we have something like this, from B to B prime, like this, we have an angle here. We have an angle here, which is delta beta. If we take, let me have this color in order to not mix things up. If we get a tangent of this angle, which is delta A here, the tangent of the new angle, which is beta prime, the tangent of beta prime is going to be delta A divided by delta beta, which is somehow, according to mathematical principles, as long as this tangent is so small, we have delta beta here equal to beta. So, when we have a velocity over here multiplied by delta t, we're going to have the location of that, because velocity multiplied by time, we're going to have the location of that. We're going to have the location of that velocity multiplied by time. This is here. So we can attribute delta beta as a tangent of that, delta A, which is x is equal to delta A, as u delta t divided by b, because we have a b here, which is the height of this area in this section. So, if we take a limit of this equation regarding delta t goes to 0, is gonna be u, let me just do this, delta b divided by delta t. With the regarding of the delta t goes to 0, we're going to have u over b. This is definition of shear strain gamma dot, rate of shear strain. You remember that I told you we have if we have a no slip condition, we can provide this limitation. Because if we don't have this no slip condition, we're going to have to apply more complex mathematical equation, which is going to be in advanced fluid mechanics. But in simple fluid mechanics, we're going to regard this as no slip condition here. So, As a result, gamma is equal to U over B, which is equal to limitation of delta T goes to 0 of delta B divided by delta T, which is delta B is equal to beta here. In another calculation, mathematical calculation, if we have gamma dot is equal to UB, in differential manner, we're gonna have du over dy, because the scale is like that, y, x. So, this is also attributed of proportionality of gamma dot to shear stress, which is tau. So, if we have tau proportional to du over dy, we have to have a constant magnitude in order to make it equation. So, we have tau equal to mu du over dy, which u is viscosity, as I told you in the instruction. Welcome back, guys. We are in the second section of viscosity. As you saw in the written text, the results indicates that for common fluids such as water, oil, gasoline, and air, the shearing stress and rate of shearing strain velocity gradient can be related with the relationship 1.9 here, where the constant of a proportionality is designated by the Greek symbol mu. It is mu. And it's called absolute viscosity, dynamic viscosity, or simply the viscosity of the fluid. In accordance with equation 1.9, plots of verses should be linear with the slope equal to viscosity for Newtonian fluids. As you see here, we have a linear slope in figure 1.6. Fortunately, most common fluids, both liquids and gases, are Newtonian. The actual value of viscosity depends on the particular fluid, and for a particular fluid, the viscosity is also highly dependent to temperature. Fluids of which the shearing stress is not linearly related to the rate of shearing strain are designated as non-Newtonian fluids. For non-Newtonian fluids, the apparent viscosity is a function of the shear rate. Guys, as it's said in the slide, fortunately, you're gonna solve the questions by assumption of Newtonian fluid. But if you will be provided by non-Newtonian fluids, they're gonna tell you. But pay attention to this term, dynamic viscosity. There's something as kinematic viscosity, which I'm going to instruct at the end of this session, but know that mu in equation 1.9 is the dynamic viscosity or absolute viscosity or just totally the viscosity. Yeah. Although there is a variety of types of non-Newtonian fluids, the simplest and most common are shown here: shear thinning, shear thickening, baking and plastic, and Newtonian, as we talked about it in the previous slide. The slope of shear stress versus rate of shearing strain graph is denoted as the apparent viscosity. There's a shearing stress here and rate of shearing strain here, du over dy. We call this graph as apparent viscosity, as stated here. For Newtonian fluids, the apparent viscosity is the same as the viscosity and it's independent of shear rate. Pay attention, guys, here. When we have Newtonian fluid, the viscosity, which I told you that is termed also as dynamic viscosity or absolute viscosity, it is either apparent viscosity because it is related to Newtonian fluids. And in Newtonian fluids, viscosity, which is termed as dynamic viscosity, apparent viscosity, or just total viscosity, it is independent of shear rate. Pay attention to this. Independent of shear rate. However, when we have a shear thinning fluids, the apparent viscosity decreases with increasing shear rate. Why? Because as you see in this picture, as we go up, the slope is going to decrease. The slope of shearing stress over rate of shearing strain, which is attributed as apparent viscosity. Which means that the harder the fluid is sheared, the less viscous it becomes. More colloidal suspensions and polymer solutions are shear thinning. Chemical engineers, which their field is process most likely, pay attention to this section. When you have polymers, means that you have shear thinning fluids, because in its graph, as you go up, the rate of the apparent viscosity, which is rate of shear stress divided by rate of shearing strain, is going to decrease, because as you go up, the slope is going to be getting near to the zero over here. But for shear thickening fluids, the apparent viscosity increases with increasing shear rate, because there's a hyperbolic slope here. As we go up, the slope is going to increase either. The harder the fluid is sheared, the more viscous it becomes. Common examples of this type of fluid include water corn starch mixture and water sand mixture quicksand. Thus, the difficulty in removing an object from quicksand increases dramatically as the speed of removal increases. From equation 1.9, it can be readily deduced that the dimensions of viscosity are thus in VG units. Viscosity is given as and in SI units as values of viscosity for several common liquids and gases are listed in table 1.5 through 1.8. A quick glance at these tables reveals that wide variation in viscosity among fluids. Viscosity is only mildly dependent on pressure, and the effect of pressure is usually neglected. However, as previously mentioned, viscosity is very sensitive to temperature. Guys, this is one of the main points of this session. Pay attention to this. When you have a viscosity, pay attention to its temperature, most likely and more importantly, because temperature, as it's saying, has a mild effect on the viscosity, but somehow temperature is more effective. So, it is to be noted from this figure here that the viscosity of liquids decreases with an increase in temperature, as you see here for glycerin, SAE, and water. Whereas for gases, an increase in temperature causes an increase in viscosity, as you see air here and hydrogen gas here. As temperature goes up, the viscosity of gases, air, and hydrogen also goes up. This difference in the effect of temperature on the viscosity of liquids and gases can be again be traced back to the difference in molecular structure. Guys, let me just see that. Share planning. Yes, we are on the right course. Trace back to the difference in molecular structure. The liquid molecules are closely spaced, with strong cohesive forces between liquids, and their resistance to relative motion between adjacent layers of fluid is related to these intermolecular forces. As the temperature increases, these cohesive forces are reduced with a corresponding reduction in resistance to motion. Since viscosity is an index of this resistance, it follows that the viscosity is reduced by an increase in temperature. In gases, however, the molecules are widely spaced and the intermolecular forces are negligible. In this case, resistance to relative motions arises to the exchange of momentum of gas molecules between adjacent layers. As molecules are transported by random motion from a region of low bulk velocity to mix with molecules in a region of higher bulk velocity and vice versa, there's an effective momentum exchange which resists the relative motion between the layers. As the temperature of gas increases, the random molecular activity increases with a corresponding increase in viscosity. So guys, as I told you in the previous session, molecular structure of fluids in terms of liquids somehow there is somehow adjacent and more disciplinized structure in liquids. And this structure also reveals that when we increase the temperature, the bounds between molecules are going to be devastated, and the molecules of liquid can move around, which means less viscosity in fluids, this structure. But in gases, the structure is somehow more or less distributed in the whole area, because the momentum of gas molecules, as it said in the text, is following some exchanges that requires to be transported from bottom layers to the other layers, and this momentum exerts some bounds for viscosity, which is going to be resulted in increase of viscosity by increase of temperature. So we reached another example. Example 1.5. The velocity distribution for the flow of a Newtonian fluid between two wide parallel plates, as seen in figure E1.5a here, is given by equation this, where V is the mean velocity. The fluid has a viscosity of 1.04 pound second per square feet. Also, V is 2 feet per second, and H is 0.2 inches. Determine A, the shearing stress acting on the bottom wall, and B, the shearing stress acting on a plane parallel to walls and passing through the certain line mid-plane here. Let me just provide you the solution in a written text. Follow me with the written text. Welcome guys to this section. Here I'm gonna solve you the example number 1.5. The parameters are viscosity, mu is equal to 0.04 pound second per square feet. Velocity is equal to 2 feet per second. And h is 0.2 inches. We have this picture. Here is a plate, and also here. There's a profile, something like that. This is the middle line. We have h here, and also h here. The scale is something like that. Yx, and this is U profile. We have to determine the shear stress in the bottom wall, as well as shear stress acting on a parallel to the walls and passing through the center line midplane. Regarding of this equation, U is equal to 3V divided by 2 multiplied by 1 minus Y over H to power 2. We can also write it as this. U is equal to 3V over 2 multiplied by 1 minus Y2 over H2. So we're going to solve that. According to equation 1.9, which was equal to tau is equal to mu du over dy. We're going to have du over dy regarding this equation by having differentiated of that equal to minus 3v y divided by h to power 2, because we have 3v over 2 minus 3v y to power 2 divided by h2. If we have a differentiate of that, we're going to have this equation. Yes, that's right. And there's a 2 also here. If we apply the bottom line for this y, we're going to have something like that. Du is equal to du over dy is equal to minus 3v. For the bottom line here, we have minus h placed as a y divided by h2. So we have this parameter 3v divided by h, because this is going to be cancelled by this and this by this. So for the bottom line, let me just do this. Yeah, tau of bottom tau bottom wall is equal to mu du over dy, which is equal to mu 3v over h. We have it as this 0.04 pound second per square feet, and multiplied by 3 multiplied by 2 over 0.2 inches multiplied by each 12 inch is 1 feet, because we have to have a unit conversion here in order to have everything in order. So doing the calculation, we have 14.4 pound per square feet in the flow direction. tau, this direction. So if we do the calculation for the upper layer either and add them up for the middle line, in the middle line we have maximum of this U profile, which means that if we have a U maximum, due to mathematical concepts, its differentiation is going to be due to everything is going to be 0. So in the middle line here, we're going to have T middle as 0. So let me just repeat this. When we have a maximum velocity profile here regarding to middle line over here, its differentiation due to everything is going to be 0 due to mathematical concepts. So tau middle is equal to 0. And the tau in the bottom wall is going to be 14.4 pound per square feet here. Welcome back, guys. We are on the 6th slide for viscosity. It is saying that quite often viscosity appears in fluid flow problems combined with the density in the form of nu, which is equal to mu over density. This ratio is going to be called kinematic viscosity. So guys, we've known that mu is for Newtonian fluids, I'm telling you. It is apparent viscosity, dynamic viscosity, absolute viscosity, and just viscosity, which if we divide it by density, we're going to have kinematic viscosity. And it's denoted with the Greek symbol nu. The dimensions of kinematic viscosity are R and the B, unfortunately forgot to tell you the units here, but I'm going to provide it to you. And in BG units and SI units, values of kinematic viscosity for some common liquids and gases are given in the tables 1.5 to 1.8. More extensive tables giving both the dynamic and kinematic viscosities for water and air can be found in Appendix B, Table B1 through B4. And graphs showing the variation in both dynamic and kinematic viscosity with temperature for a variety of fluids are also provided in Appendix B, Figures 1B1 and B2. So, there is compressibility of fluids. Guys, let me just tell you that in this section, we're just going to be through subsection of 1.7.3 speed of sound. This is mainly due to the fact that when I was in bachelor time, they didn't provide us real details of 1.71.1 and 1.7.2, which were about bulk modulus, which speed of sound is going to be attributed from bulk modulus, but we don't have really serious to do with it. Just learn this equation, which C is speed of sound is equal to K RT, which K is a constant, and R is a molecular feature, and T is temperature. And remind that you have to get absolute temperature. Somehow it is demonstrated to be degree of Rankine, but in the text there was degree of Fahrenheit, which I myself didn't realize why this is such a thing, but accepted as a rule that speed of sound is going to be square root of K, which is a gas constant for ideal gases, RT. So we are on slide 15. There are 7 slides left. Let me bring it up. Vapor pressure. It is a common observation that liquids such as water and gasoline will evaporate. If they are simply placed in a container open to the atmosphere, evaporation takes place because some liquids molecules at the surface have sufficient momentum to overcome the intermolecular cohesive forces and escape into the atmosphere. Guys, you have absolutely seen that when you put a container of water or gas or any kind of liquid at the side, after a while after going and back, you're gonna see some part of it is lessened or decreased. It is this occurrence that is taking place, evaporation, and momentum of overcoming intermolecular cohesive forces and to the atmosphere and escaping to the atmosphere. If the container is closed with a small airspace left above the surface and this space evacuated to form a vacuum, a pressure will develop in the space as a result of the vapor that is formed by the escaping molecules. When an equilibrium condition is reached so that the number of molecules leaving the surface is equal to the number of entering, the vapor is said to be saturated, and the pressure that vapor exerts on the liquid surface is termed as vapor pressure. You know, guys, when we keep the liquid in a container by fastened a gate above it, if there is a small hole somehow on the top, there is a less rate of escaping vapors, but it actually exists. This existence of escaping gases is going to provide some pressure. When the rate of getting out and the rate of entering bubbles of air are equal, which means equilibrium condition, as it's said in here, there is a pressure difference, which is vapor pressure. Similarly, if the end of a completely liquid filled container is moved without letting any air into the container, the space between the liquid and the end becomes filled with the vapor at a pressure equal to vapor pressure. So it means that whether or not we fasten any container by bottom or upper layers, the vapor pressure is ultimately be let me just find the right word. It's going to be provided. You know, because intermolecular interactions of the fluid is going to provide this vapor pressure by passing the time. In some industrial units, they're going to remove the vapor pressure by plugging some doors in the storage tanks, most likely to remove the vapor pressure. This is the point. I might provide you some videos in order to give the details to you, in order to, and I'll provide some videos for you to give you the details of the vapor pressure removing. I might provide it in the Telegram channel. Vapor pressure part 2. Since the development of a vapor pressure, let me just verify where we are. Slide 16. Yeah. Since the development of a vapor pressure is closely associated with the molecular activity, the value of vapor pressure for a particular liquid depends on the temperature, as it's shown. No, it's something else. Values of vapor pressure for water at various temperatures can be found in Appendix B, Tables B1 to B2. And the values of vapor pressure for several common liquids at room temperatures are given in Tables 1.1 and 1.6. Boiling, which is the formation of vapor bubbles within the fluid mass. It is initiated when the absolute pressure in the fluid reaches the vapor pressure. Guys, when the pressure of the fluid is equal to the vapor pressure of the fluid, the bubbles are going to be created and formed. And it's initiated. As commonly observed in the kitchen, water at standard atmospheric pressure will boil when the temperature reaches. That is, the vapor pressure of water it is 14.7 psi absolute. However, if we attempt to boil water at a higher elevation, say something like 30,000 feet above sea level, the approximate elevation of Mountain Everest, where the atmospheric pressure is 4.37 psi is absolute, we find that boiling will start when the temperature is absolute 157 degrees Fahrenheit. The boiling temperature is a function of altitude, which is here. This diagram means that as we go up, the altitude increases, the boiling temperature decreases because it is related to the temperature decrease and pressure decrease. Thus, boiling can be induced at a given pressure acting on the fluid by raising the temperature, or at a given fluid temperature by lowering the temperature. An important reason for our interest in vapor pressure and boiling lies in the common observation that in the flowing fluids it is possible to develop very low pressure due to the fluid motion. And if the pressure is lowered to the vapor pressure, boiling will occur. For example, this phenomenon may occur in the flow through the irregular narrowed passages of a valve or pump. When the vapor bubbles are formed in a flowing fluid, they are swept along into regions of higher pressure, where they suddenly collapse sufficiently intensely to actually cause structural damage. The formation and subsequent collapse of vapor bubbles in a flowing fluid called cavitation. It is important fluid flow phenomenon to be given further attention in chapter 3 and 7. You know, guys, let me just tell you that when you have a valve in an industrial unit or pump, as you lower, as the pressure is lowered to nearly vapor pressure, bubbles are going to be formed in the area around the valve, which you may have seen sometimes. This action is going to be caused ultimately to the cavitation, which bubbles are going to be distributed all around. Let me just bring you let me just bring a video to you to demonstrate the cavitation in details. Please pay attention to this video.
Here we have a pump trainer. We have an electric motor with a horsepower meter through a magnetic coupling to a centrifugal pump. The pump itself is made of acrylic, so we can see the spinning impeller inside. We can also see the fluid go through. It's got a gate valve here on the discharge. It's got another valve over here on the suction. And all the piping here is clear, so we can watch the flow of fluid. But right now it's all clear water, so we can't see much in that regard. It's got a rotometer here showing us the amount of flow. But what I'm going to demonstrate here is cavitation. We're going to purposely cause cavitation to occur in the system. We're going to do so by keeping the discharge valve wide open like it is and pinching off the suction valve. What that will do is reduce the pressure of this line, and you'll see this compound gauge show a stronger and stronger vacuum as we begin to pinch off this valve. Now start to turn this clockwise, and you will see the gauge's indication go down. You'll also begin to hear cavitation take effect, and we'll be able to see the bubbles form inside of here as it cavitates after it flashes in the vapor and cavitates into liquid again here. So here we go, closing the valve. And watching the gauge. Gauge will go down. Minus 10 inches of mercury. Minus 12. Minus 14. You can start to hear flashing occur there. 16. More noise. Minus 18. Minus 20. You start to hear that sounds almost like rocks going through the pipe. There's no debris, there's no solid material through here. That solid sounding sound is really the collapsing of the vapor bubbles as they go back into liquid form. You can really hear it now. You can see it occur inside of here. It's a very pronounced action and noise. As the water goes through the valve, it reduces pressure going through the restricted valve. Its pressure drops below the vapor point of the water at this temperature. It flashes into steam, and then after it comes out of the valve and expands again, the pressure goes up, and what happens is those vapor bubbles collapse back into liquid, and that's when we get the cavitation effect. We can see it happening here. We can also see some bubbles here in the scroll casing of the pump. Cavitation is very destructive, especially upon metal surfaces. The acrylic surfaces here seem to handle it a little bit better, but with metal surfaces, there's no give, and it's very destructive. The metal will become pitted by the high pressure jets formed by the collapsing bubbles. So I just want to illustrate what cavitation looks like in an acrylic tube and what it sounds like. Sounds like rocks, literally like rocks going through the pipe. And again, we cause it by dropping too low of a pressure, causing flashing to occur, and when the pressure rises again, the bubbles collapse, and that's when cavitation occurs. I will open this valve back up. That increases the pressure on the suction side of the pump, less and less vacuum, until we no longer flash, and we no longer cavitate.
Welcome back, guys. Guys, in this part of instruction, I'm gonna give you the whole text of surface tension 1, 2, 3, and 4, and then I'm gonna provide you handwriting text in order to illustrate everything to you in written text. So, at the interface between a liquid and a gas, or between two immiscible liquids, forces develop in the liquid surface, which cause the surface to behave as if it were a skin or membrane stretched over the fluid mass. Although such a skin is not actually present, the conceptual analogy allows us to explain several commonly observed phenomena. For example, a steel needle or a razor blade will float on water if placed gently on the surface because the tension developed in the hypothetical skin supports it. Small droplets of mercury will form into spheres when placed on a smooth surface because the cohesive forces in the surface tend to hold the molecules together in a compact shape. Similarly, discrete bubbles will form in a liquid. These various types of surface phenomena are due to unbalanced cohesive forces acting on the liquid molecules at the fluid surface. Molecules in the interior of a fluid mass are surrounded by molecules that are attracted to each other equally. However, molecules along the surface are subjected to a net force toward the interior. The apparent physical consequence of this unbalanced force along the surface is to create the hypothetical skin or membrane, membrane. A tensile force may be considered to be acting in the plane of the surface along any line in the surface. The intensity of the molecular attraction per unit length along any line in the surface is called the surface tension and is designated by Greek symbol sigma. For a given liquid the surface tension depends on the temperature as well as the other fluid. It is in contact with at the interface. The dimensions of surface tension are the BG units of and SI of unit values of a surface tension for some common liquids in contact with the air are given in tables 1.5 and 1.6 in Appendix B, tables B1 and B2 for water at various temperatures. As you see, the surface tension decreases by increase of temperature. So you see this picture here. If the spherical drop is cut into half as shown here, the force developed around the edge due to surface tension is 2 pi r sigma. This force must be balanced by the pressure difference delta P between the internal pressure Pi and the external pressure Pe acting over the circular area P r squared. Thus, we have this equation. Don't worry about it, guys. I'm going to provide it in handwriting text totally. There's just 2 slides left. It is apparent from this result that the pressure inside the drop is greater than the pressure surrounding the drop. Would the pressure on the inside of a bubble of water be the same as that inside of a drop water of the same diameter and at the same temperature? Among common phenomena associated with surface tension is the rise or fall of a liquid in a capillary tube. If a small open tube is inserted into water, the water level in the tube will rise above the water level outside the tube, as you see here. Guys, I'll provide some videos along with the written text in order to illustrate everything to you. In this situation, we have a liquid gas solid interface. For the case illustrated, there is an attraction, it means adhesion, between the wall of the tube and the liquid molecules, which is strong enough to overcome the mutual attraction cohesion of the molecules and pull them up the wall. Hence, the liquid is set to with the solid surface. The height h is governed by the value of surface tension. The tube radius r, the specific weight of the liquid, and the angle of contact theta between the fluid and tube. From the free surface body diagram, figure 1.10b is provided, which means here, which I'll also provide in the written text. Surface tension part 4. We see that the vertical forces due to the surface tension is equal to 2 pi r sigma cosine theta, and weight is gamma p r square h, and these two forces must balance for equilibrium. Thus, we have this equation. The angle of contact is a function of both the liquid and the surface. For water in contact with the clean gas, theta is some relatively equal to 0. If addition of molecules to the solid surface is weak compared to the cohesion between molecules, the liquid will not wet the surface, and the level in a tube placed in a non-wetting liquid will actually be depressed, like this. So, let me just give you the texts of example 1.8, and then I'll go to handwriting section. Pressures are sometimes determined by measuring the height of a column of liquid in a vertical tube. Find the diameter of a clean gas tubing is required so that the rise of water at 20 degrees Celsius in a tube due to the capillary action as opposed to pressure in the tube is less than H equal to 1 millimeter. Now, guys, is the time of written text to give you whole details of surface tension from 1 to 5. Let's go for the written text. So guys, welcome to most exciting section of this instruction section for surface tension. In order to provide you the details of this calculation for surface tension, let's assume we have a droplet which is divided into pieces. We have something like that. This is a droplet. There is a pressure difference here, delta P, and there is a surface tension sigma here. This is a radius, and this sigma is distributed all over this area. Sigma, sigma here. The force inserted in this section is going to be delta pi multiplied by PR2, because the cross-sectional area is circle. The area of circle is going to be delta pi r to power 2, which we multiplied by delta p is going to be the force. But this force, in order to keep the droplet in equilibrium, has to be equal to 2 pi r sigma, which is sigma is exerted from here. Why 2 pi r? Because the sigma is exerted on the sided area. The sided area of cylinder is 2 pi r. Of a droplet, excuse me, not a cylinder. If we have this equation equal to this side, delta pi is equal to, the force is equal to delta pi r2 is equal to 2 pi r sigma. This r is going to be omitted by this, pi by this, and we have delta pi is equal to sigma over r, which is pi I minus p e. So this is the part one of the surface tension for droplets. But if we have something like this, let me just have the picture in front of me. When we have something like this, and there's a fluid over here, and the surface tension is into this direction. There's a theta over here. There's an angle over here. So, and there's a weight force over here. In order to have the equilibrium here, we have to have and excuse me, just let me just provide the parameters right, h, and the force in this direction. As I told you, from this part, force is exerted on the sided area. So the force is equal to 2 pi r sigma, which is have to be equal to with weight. in order to have everything in equilibrium. Yeah, here. The weight is equal to mg, which is rho vg, which is rho g v. The v here is pi r to power 2h because the because the force is exerted on the sided area of the cylinder. This is a cylinder, just consider it as a cylinder. So we have 2 pi r sigma equal to rho g pi r to power 2h, which, as you know, rho g is gamma, which is going to be multiplied by pi r to h here. But as we have an angle over here, we have to merge it on this side, on this scale. So we have 2 pi r sigma cosine theta is equal to excuse me, is equal to gamma pi r to power 2h. So if we do the calculation, we're going to have h is equal to 2 sigma cosine theta over gamma r. We have r omitted by this and pi omitted by this. If we do all the calculation and provide it in detail, we're going to have this formula. This formula is so important. There's just one more detail in order to give you. Sometimes for some fluids like mercury, we have this as this. The hyperbolic side is to the downside, opposing to this, which is to the upper side. It is due to features of the material and the fluid we have used. For mercury, it's going to be something like that, which theta is going to be 130 degrees. But for water, the theta is 90 degrees, or something like that. Sometimes it's smaller than 90 degrees. Let's go for the example 1.8. Welcome guys to example number 1.8. Example number 1.8. We have the parameters as temperature is equal to 20 degrees. The height has to be 1 millimeter, and there's no other parameters. There's a clean glass, and we want to provide the diameter which we can achieve. H equal to 1 millimeter when we put the tube in the water. When the water climbs up, we're going to have 1 millimeter through which diameter? The question is this. Diameter is equal to a question mark. So, according to equation 1.22, which was this, I forgot to tell you about that in the previous written text. In in the previous written text instruction. H is equal to 2 sigma cosine theta gamma divided by R. If we have the R extracted, R is going to be equal to 2 sigma cosine theta divided by gamma H. At temperature of 20 degrees, according to table B2 at the end of the book, we're going to have sigma is equal to 0.0728 Newton meter. And gamma is equal to 9.789 kilonewtons per cubic meter. For the clean glass, excuse me, theta is 0, which means that if we have a water for the clean glass, the angle of exerted sigma is going to be 0, which means cosine 0 is going to be 1. So we have R just is equal to 2 sigma over gamma H, which means that 2 multiplied by 0.0728 Newton per meter divided by 9.0786 multiplied by 10 to power 3 Newton per cubic meter multiplied by 1 millimeter, 1 multiplied by 10 to power minus 3 in order to have everything in meter. Doing the calculation, we're going to have the R is equal to 0.149 meters. If we want to have the diameter, we just have to multiply R to 2 R's, which is going to be 0. Excuse me, guys, I forgot to do this. Excuse me. 0.298 meters, which is going to be 29.8 millimeters. As long as I forgot to pick the picture at the top to pull everything up in order to give you the details, we have 2 sigma, which is 0.0728 Newton per meter, divided by gamma H, which gamma is going to be 9.789 multiplied by 10 to power 3 Newton per cubic meter, and we have a height of 1 millimeter here, which is going to be 1 multiplied by 10 to power minus 3 meter. Doing the calculation, we have excuse me, yeah, everything is all right. R is going to be 0.0149 meters. If we multiply it by 2, the diameter is going to be achieved, which is 0.298 meters, which is 29.8 millimeters.
Welcome back, guys, to the last section. Surface tension effects play a role in many fluid mechanics problems, including the movement of liquids through the soil and other porous media, flow of thin films, formation of drops and bubbles, and the breakup of liquid jets. For example, surface tension is a main factor in the formation of drops from a leaking faucet, as shown in the photograph in the margin, which I didn't provide it here. Surface phenomena associated with the liquid-gas, liquid-liquid, and liquid-gas-solid interfaces are exceedingly complex and more detailed and rigorous. The discussion of them is beyond the scope of this text. Fortunately, in many fluid mechanics problems, Surface phenomena as characterized by surface tension are not important, since inertia, gravitational, and viscous forces are much more important. So guys, as we have seen, we have more highlighted forces to be paid attention, such as inertial, gravitational, and viscous, which means that we have neglected other external forces to be highlighted as most important ones. So guys, there's the end of this session. I hope you have followed the subjects really well. I'm going to provide you the end of chapters problems, some of them actually, in order to embed everything into your mind correctly and sufficiently. Follow me with the problem solving section.